Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Hope you guys are fine. Can you hear me?
Yes, doctor. Good morning.
Morning. Okay, good. I hope everybody is not affected by the floods here in Malaysia. If you are, let us know, so that we can at least try to ease some of your studies here in UTM maybe. So today we will be starting to look at multi-component distillation, which will not be tested in test test 2, but it will be coming out in the final. Okay? And also you need it for your project. So your project, you are supposed to design the 2 distillation column using the shortcut method. That's what we're going to discuss here, the shortcut method. We're not going to do the shortcut method. Is just an approximation. It's not giving you the accurate answer, the accurate design. So you will need to do a rigorous method in order to get a better design. So by right, if you're going to design, for example, those doing the plant design, you can start with shortcut method, but that is just for you to begin with. You start with shortcut method and then you proceed to the rigorous method. Okay, so you cannot use the shortcut method for design. It is not accurate. Okay, we will wait a few more minutes for the others to join us. So far, I have 45 students scanning the QR code. So any questions you want to ask before we start looking at multi-component distillation? Your test 2 will be on the 19th of the January. That's quite close to the end of the semester. The semester will end, I mean, not the end of the semester, before your exam week, the break. Your exam will start in early February. Okay, for our subject, it is proposed to be on the 8th of February. Okay, on the 8th of February will be your final. That's the proposed date. And you will have a week break before that. So we should finish the whole syllabus by the 31st of, 31st of January. Yeah, so we have roughly 5 weeks to cover that. Inshallah, we'll be able to make it, but if we are short of time, I might have to call for an extra class. And so your second test will cover McCarthy method, the method that we have done using the graphical method. It is only for binary components, for binary mixture. So you only have two components, and most of the time, you'll be looking at just the typical, the look at the example that we have done. It will be mostly that, unless the lecturer said it in a deep, she got something that is slightly different. Maybe it will be slightly different, but then it will still be graphically the same McCaptil method. Okay, so you should have a proper graph paper. There's no excuse at all for those that don't have graph paper. You have been informed ample times, and I mean, you got ample time. You are informed earlier, and informed early, so there's no excuse at all to say that you don't have any graph paper. I'll foresee that you're not going to get pre plotted graph. You will be doing it by hand plotted your graph. You will be plotting your graph by hand. So you will have two graphs that you need to prepare. One of it is for the liquid extraction, and liquid extraction is kind of a bit messy compared to McCaptil. You will come across it later once we finish multi-component distillation. So liquid extraction involves two graphs for you to solve one problem. That means if you have the test two will be, you'll be looking at three graphs. So be ready. Just be ready with the graph, the outline of it. You should know the McCaptil. You have the x and the y axis from 0 to 1. You should have at least a 45-degree line plotted, and that kind of things. Because you don't know the system, what is coming out. There's no way of predicting it. It could be anything out of the A, that is going to come out. So just be ready that you need the graph. The graph should at least have the x and the y axis and the 45-degree line plotted. Same thing for the liquid extraction. You kind of know how you're going to be. You kind of know what to get ready. Okay, so okay, now I've done. I think I stop here sharing the QR code. We need to look at the multi-component distillation. Okay, as you can see from the screen, I have two slides side by side. Before this, we have looked at binary distillation. So the binary distillation is on the left-hand side. Now we're going to look at multi-component. Before that, I better record the lecture. Hey guys, we'll be looking at multi-component distillation. So we have already mentioned the enthalpy concentration method. So I kind of briefly go through it last Sunday. Right. So now we're going to look at multi-component distillation, and this is what is happening in the outside world, in the plant. We're not going to have binary distillation. Most of the time, it is multi-component distillation. So when we mention multi-component distillation, that means it has more than two components in it. For example, if you look at the figure that I have over here, I have component A, B, C. A, B, and C, that's three components. So when you have three components, you will need two distillation column. The calculation is like this. The number n minus 1. Okay? So n is the number of components. So if you have three components, that means 3 minus 1, then you need two distillation column to separate the mixture. Okay? So in this case, let's look at the separation going on. You have component A, B, and C in the fit. Normally, you arrange it in order of volatility. Okay, so the most volatile will be A, and B will be the intermediate, and C will be the least volatile, meaning it is in order of decreasing volatilities. So you will split between C and B first. You split between B and C, so C will go into the bottom of the first column, and you will have your top product mixture of A and B. And then in the next column, then you will split A and B. So there's a sequence to it. So how do you go about it? We will look at the shortcut method. As I mentioned earlier, the shortcut method is just an approximation. So do not use it in your design, in your final design. It can be used in the plenary of the design for you to have something to start on before you get into the rigorous method. Because if you start with the shortcut method, you have at least something to save. It will save you lots of time when you do it the rigorous method using your computer, the software. It will save you quite a lot of time. So this shortcut method is useful. So how do you we need to define a certain term first. We will give the term heavy key. Heavy key, that's for the component that will be in the bottom. Oh, sorry, not. Let me rephrase that. The heavy key is where you have your two separate Okay, let me start all over again. You will look at heavy key and light key. In the textbook, we use the nomenclature H for heavy key, L for the light key, but some textbook they use light key, heavy key. But in our textbook, we're going to use light key, just L, and here we're going to use just H for the heavy key. So in our example here, we have A, B, and C. If you look at the first column, the split is between C and B. This is the split because A and B is going up, C is going down in the bottom product. So your heavy key will be C and your light key will be B. That is how you define it. Okay, where the split is, the component that goes into the bottom will be the heavy key, and the component that will be in the top, that is next to the heavy key, will be your light key. Okay? And then within the next column, you only have two split between A and B. So now between A and B, the split is just between the two of them. So B will be your heavy key and L will be your light key. Okay, so now let's go back to the first column. In the first column, you have component A and B at the top product, which is in the distillate. So what is component A then? Component A is referred to as the light component. It's not the light key. It's not the light key. It's the light component. So this is your light key. This is your heavy key. If I use the K to denote key. So your component A is the light component because it is lighter than the light key. Okay, so that's how you define the components, which you will utilize when we do the calculation later on. Okay, so let's go through this. You have the light component, which is like more volatile than the light key. The heavy component, if you have another component, for example, A, B, C, D, then the D component D will be the heavy component. That is, it is less volatile compared to the heavy key. Right? So that's how you define the components. We will look at it more in the example. Now, before we start looking at the calculation, we will review our Rao's law, revisit it. Rao's law, if you recall, we have Rao's law over here, okay, where when we were looking at binary, okay, this is Rao's law. So your Rao's law is for an ideal system. For an ideal system. Okay, if it's not ideal, then you cannot apply Rao's law. So in Rao's law, you have your vapor, let me see, this is vapor pressure. I don't want to get confused. This is vapor pressure, capital P. Okay, so that's vapor pressure. And obviously that is your total pressure. There should be a small p, and that is for partial pressure. So let's go back to our multi-component. And this is your partial pressure, the lowercase p. That's your partial pressure. And the capital P with the subscript, that's your, let me highlight it, that's the capital P with the subscript. Yeah. That is your vapor pressure for that component. That is your vapor pressure. So obviously the capital P without any subscript is the total pressure. So this is how you calculate the relationship, the vapor liquid equilibrium between the components. Sorry, not between the component, the vapor liquid equilibrium for each component. Okay, so for example, for component A, that's in the vapor, and for the liquid that is in equilibrium with that vapor, you calculated it using Gauss law. The relationship is as shown here, where YA is equals to the vapor pressure of A divided by the total pressure times by the mole fraction of the liquid that is in equilibrium with the vapor. Yeah, so that's how you calculate the equilibrium relationship between Y and X of the same component. Provided it is ideal, then you use the Gauss law. But normally, if it's not ideal, for example, when you are looking at hydrocarbon system, you will not use Gauss law. You will use the equilibrium, or what we refer to as the vapor liquid equilibrium constant. Another term for it is the distribution coefficient. And that is capital K. So for every component, you will have the subscript for that component. So if it's component C, then the subscript is C, and so forth. So this value, if it's ideal, if your system is ideal, then you will be using this equation where your vapor liquid equilibrium constant is equal to the vapor pressure divided by the total pressure if it's ideal. But if it's not ideal, then you will have to find that value of your K constant or your vapor liquid constant. And normally, your vapor liquid constant, they are given in a graph, or you can even have it in a table form, whereby you can calculate it. Okay, so let's look at the graph. Over here, you have the equilibrium constant for just 4 components. These are the 4 components that we're going to look in the example, that we're going to calculate in the example, that we're going to the example given for the component given for the example. Okay, so you can get the equilibrium data, the VLE or the K constant, but that constant depends on the temperature. So your x-axis is the temperature and the K is the y-axis. So depending on what temperature you choose, then you'll be able to get your equilibrium constant. Okay, so you can also use this graph. This kind of weird. Okay, now let's look at the graph that over here. This graph is specifically for 405.3 kilopascal. That is about 4 atm. Because the K value, the K constant, the equilibrium constant depends on temperature and pressure. So if you have only at one temperature, if you need more than one pressure, then you need more than one graph. If you're looking at the left-hand side, that type of graph on the left-hand side. So in order to avoid that, over here you have the left-hand side is the pressure, the right-hand side is the temperature. And what is the K constant? The K constant is the value that is, that look like that's on the left-hand side, on the right-hand side of look like the ruler there. Okay, let's look at an example. For example, I have the pressure of 400 kilopascal and the temperature of about 25 degrees C. That's about 25 degrees C there. Okay, and I wanted to find, for example, let's look at this here. At 25 degrees C, where is 25 degrees C? That's 25 degrees C, and that's the pressure. That is 4 atm, 400 roughly. Let me find something that is easy to read. Okay, let's for N hexane. So what is that value? This is 0, 6, 7, 8, 9, 10. Okay, that's about 0 0.06. If I use this graph on the left hand side, but if I look at the graph on the right hand side, okay, I have the pressure already here on the left side, 400. I cannot get it so accurate as 405 because the scale is very, you know, I don't think I can get 100. That's roughly about 405, roughly. Okay? And the 25 degrees C is there. I'm looking at N hexane. Can I look? Where is my N hexane? This is my N hexane. Oops. My N hexane is here. So I'll be looking at this line to get my K value. Okay. So if you zoom in, that's about, because my line is too heavy, the solid line is heavy. So it's, if you read it off the graph, it's about roughly 0.07. Okay, it's roughly 0.07. But the value that we got from this graph, which is more accurate, it's about 0.06. So it's not too far off. Okay? If you use this graph, it will be more accurate because of the scale. But if you use this graph, because of the way the scale is written, it's kind of difficult to get it that 0.06. You have really need to zoom in, and I don't think I can zoom in that far. I don't think I can do that to get 0.06, but you get roughly the idea that is about 0.07. So that's one way of doing it. You can have the left-hand side graph or you have the right-hand side graph. Or another way is to calculate it using the equation here. These equations, they are specifically for light hydrocarbon. So you have the value of A, B, and C, and D. And the form that you're going to use, you have so many forms, 1, 2, 3. So if you have N hexane, okay, so N hexane you're supposed to use form 1. That means you'll be looking at just that one equation, the top one. Okay? So your temperature should be in degrees ranking, and your pressure should be in PSIA. So if you want to calculate for N hexane, it's like how we obtain it using the two graphs. You can do so by putting in the value of your A there, your B, okay, your C, and again the pressure must be in PSI. Before this we look at the example 400 kilopascal, so you need to convert it to PSI. And the temperature that we were looking at previously, the example is 25 degrees C. Now you need to change that to degrees ranking. And then you should be able to get your K value from the equation. So you have these three methods of getting the K or the equilibrium constant for a hydrocarbon system. Yeah, for hydrocarbon system. Any questions so far? Any questions so far?
Doctor,
Yes.
there are two equations that use this. So which one we must use? One
Sorry.
and two.
Can you repeat that again?
There are two equations, right? Ln K, D over P squared, and or D over P. So which one?
It depends on you look at this column. It's already
Okay.
stated. You can see that which equation they're going to use. 1 or 2 or 3. Depends on which system you're referring to. For the example that I just did, N hexane, I'm supposed to use equation number 1. So equation number 1 is this. It's already given. Okay.
Okay.
Any other
Thank you,
questions?
doctor.
Any other questions? Sometimes you just you're lucky enough just to get the graph. So using the graph, you will not get that accurate. It's just an estimate exactly how was the value, because just like I said, I'm using hexane now. It's 0.06. Okay, fortunately for me, it's about 0.06. But if I'm using, for example, n hat 10 is over here, then that is about, I need a rough estimate of exactly where it is. You know, nobody will get the same answer, same value. Okay, so same thing with the graph over here. Nobody is going to get the same value because first of all, you have the scale on the left hand side and the pressure scale, and then you have the pressure, the temperature scale, you know, that will add up to the error, and the next part is the K value itself. So it's just, if you're using the graph, it's just an approximate. But if you're using the equation, everybody should be getting the same value then. There's no way you can get it wrong unless you plug in the wrong value in your calculator. Yeah. So that's how you get your K value. So let's go back to our notes over here. There's another term that we are very familiar with, the relative volatility. Yeah. You have done it, you have looked at it before. We have looked at it when we're looking at binary. So that's the relative volatility when we are looking at binary. Only two components, the vapor pressure of A divided by the vapor pressure of B. Okay, that is how you calculate your relative volatility. So if you're going to do it for multi-component, instead of vapor pressure, you're going to have your K constant. Your K constant, for example, for A, and now you have a reference K value. You choose value you're going to select as your reference component. For example, over here you have component A, B, and C. So let's say you choose it to be Kc as your reference. So that this equation will become Ka over Kc if your component C is your reference. And you do the same thing for the others. Your constant, equilibrium constant divided by Kc if your component C is the reference. So this value of K, the value of the K constant, you obtain it from the graph or you calculated it using the equations. So this is how you calculate your relative volatility. Okay? But sometimes you are given, the value of the relative volatility is given. For example, I'm just giving an example. I come across this somewhere. Right? For example, this is your three component. Not good. Let me bring this down. This is your component A, B, C, and over here you have, for example, your relative volatility. So it should be given, for example, a certain value. If your C component is the reference component, then this should be 1. Kc over Kc. Alpha C is equal to the K constant divided by the reference constant. So that's 1. That will give you 1. So that's 1. For the others, the value should be higher because C is the least volatile. So for example, if this is 6, maybe this is 5. Just a value that I plug out of thin air. So this is roughly sometimes is given in. You know, you already have it calculated and the value is applied to you. You don't have to calculate the relative volatility. Right now, the relative volatility here, this is C with C, this is B compared to C, that A compared to C. That's the value. So if you look over here, if you look at the binary system, you have the A and B. Here you have the A compared to B. Okay? How volatile is component A compared to component B? So when you're looking at when you're looking at multi-component, so you have to select one component as your reference, and you will be comparing that component to the reference component. And so you will be looking at that too in the example. Okay, so before you can proceed to do your calculation for the number of stages, for the minimum reflux ratio, the question, they are similar. Yeah, you'll be asked, what is the minimum reflux ratio? What is the minimum number of stages? What is the theoretical number of stages? Where is the feed location? They are similar as binary. The question, they are very similar as binary. It's just that now you'll be dealing with more components. So before you can proceed to do that, you need to know how to calculate the dew point and the bubble point. Okay, the bubble point is for the, I'm going to close this. Okay, the bubble point is for the bottom product because they are mainly liquid in the bottom product. So you need to know the bubble point. And for the top product, which is your vapor coming out from the column, from the top column. So from that vapor, you need to calculate its dew point. Okay, so how to do it is by try and error. Unfortunately, why is it by try and error? Because you have many components, and most of the time you only have a set for the light key and the heavy key is already set. How many percent will be in the top product? How many percent will be in the bottom product? How many percent will be in the distillate? How many percent will be in the bottom product? So you know the percentage of your heavy key and your light key, meaning the percent from the feed, the amount that is fed. So how many percent of it will go into the top distillate? How many percent of it, of that component, will be in the bottom? So most of the time, you have only the light key and the heavy key set. For the other components, the one that is more volatile than the light key, the one that is less volatile than the heavy key, they are not set. Because they are not set, then you don't know exactly. You have to assume a certain assumption. You have to make certain assumption. When you make certain assumption, it becomes trial and error. And then you have to check back whether your assumption is valid. So it becomes a trial and error process. Okay, so in order to calculate the bubble point and the dew point, you have to assume a certain temperature. And at that assumed temperature, you will get your K value from the graph or from the equations. You get the K value, and from the K value, you will calculate your relative volatility. Okay, and you will know when you get the correct assumption when the temperature that you set or you assumed earlier is the same temperature that correspond to the K, the value of the K that you use as your reference. Okay, let's look at, for example, the bubble point. Okay. In order to get the correct temperature for your bubble point or your boiling point, you must satisfy this equation. Okay, so your summation Y, that is the amount of you have multi-component, so that's why there's summation. There's A, B, C, D, for example. So your mole fraction of your Y definitely is equals, the summation should be equals to 1, because you obviously that is mole fraction. The total of it should be 1. There's another equation whereby the summation of the K values times by the mole fraction of the liquid composition should also be equals to 1. And roughly, and again, you have this equation, the K reference, the component that you choose as your reference, and the summation of this product, which is your relative volatility, times by the mole fraction of your liquid, should be also equals to 1. So let's look at the step. You assume one temperature, the boiling point temperature. You just assume. Okay? From that boiling point temperature, from the graph, you can get your K values, or you can get using the equation, you can get your K value. And from the K value, you should be able to calculate your relative volatility. You set one reference, one component as the reference. For example, component C, yeah, as the reference. So now, what you have to do, you have to tabulate your, because you're going to use, let me erase this first. You're going to use this, hold on. You're going to use this part of the equation to check whether your assumption is valid. Okay? So you're going to tabulate your result, your calculated value. For example, T is equal, this is the assumed temperature. Okay? Your component A, B, and C. And you're going to get your K value. You're going to get your alpha value for every component. Okay? And then you're going to you also need to have the X component. Now we are going to find the bubble point. So you're going to get, this is for the bottom. We have a liquid here. We have a liquid for the bottom composition. For the bottom composition, so let me project. Let me continue with the graph. I need to put the composition of the bottom first. That's the composition I for every component. Okay, and then at that assumed temperature, at this assumed temperature, I should get my Ki for every component. And from that Ki, I should calculate my alpha, which is Ki over my K reference. For example, my K reference is Kc, so this will become 0. Okay? And from there, I should proceed to get, okay, the next column should be alpha times by Xi. Okay? So that's the next column. And I should get the summation, because here you have the summation. Okay. Now, I should get the calculated value. I should get this whole thing should be calculated based on the summation that I got here. Okay. I should get it based on that summation. I should get it. Okay. And from that calculated value, from that calculated value of this equation, I should be able to get my corresponding temperature, because that value here not equals to 1. Sorry guys, not equals to 1. Hold on. Let me explain all over again. Okay, the equation is like this. Summation alpha I xi equals to 1. So your K reference should be 1 over summation alpha I x1. Okay, so you already know what is your, for example, you set this to be Kc, component C. So from the graph just now, from this graph, for example, this is your A, this is your B, this is your C, and then D. So this is your component C. So you already know what is your K from this calculation. From this calculation, you already know what is the K value, which is the summation of that. Okay, so your K should be the inverse of that summation that you got here. Okay, so it should be the inverse of it. So once you get that, you will know that K value, and from that K value, for example, that K value is, for example, say 1. Okay, for example, just an example. So you will go to that corresponding component and get the corresponding temperature from the graph. From the corresponding temperature from the graph. So I will show you guys the example that that is in the textbook. That is easier to understand. Yeah, so let me tidy up so that we can look at the equation. I'm going to copy this. Look at the example. Over here we have the example. Over here you have a liquid feed, pressure, your composition of the feed, that's component A, that's component B, that's C, and that's D. Now you're supposed to calculate the boiling point. All right? So I'm going to go to the solution here. Yeah, now this is my, okay, this is my boiling point. Yeah, I'm going to assume this as my first assumption, my boiling point. Oh, I already have the, let me put the equation over here. This is the equation that we were looking at for boiling point. Okay. So from that equation here, from this equation here, oops, from this equation here, I will end up with that equation here. Or if I rewrite it, it will become K reference is equals to 1 over summation alpha I xi. If you don't understand, please ask. I might be going too fast or something is confusing to you guys, please ask. Okay, so now my first, because it's a try and error method, I will assume a temperature. So I will assume that this is my temperature, which is 132. That's my boiling point temperature that I assume. Okay. So at that boiling point, 132. So if I use the graph, if I use the graph to find 132, 132, where is 132? Let's look at the scale of our graph here. That's 125, 130. So this interval, if you look at here, okay, that interval is 110, 120, 130, sorry, I got it wrong. That's interval of 5, isn't it? Interval of 5, because 100 and 125. There's 5 intervals, so it's about, that's 105, isn't it? 105. This is 105. 110. 115. 120. Okay, that's so this here is about 130. Okay. So my assumption is 132. So it's quite close to 130, but not on 130. So if you can look at it, the scale, the graph, it's not on 130. It's about 132 there. Okay. So at 132, for every component, I have component A here. That's B. That's C. And that's D. So for every component, I need to get the K value from this graph. Okay, so let's look at the K value that I obtained for component A at 132 degrees C. This is my K value for my component A. And I do the same thing for component B. I got 2.35, is that it? 2.35, roughly, if you look at the scale. And for component C, I got 1.15. And for D, I got 0.61. So I will put it in the table form, the K value that I got. This is for component A, B, C, D that I read off from the graph at a temperature of 132, the temperature that I assumed earlier. Okay? The temperature that I assumed earlier, which is 132. The composition that is given is the composition of the feed. This is your composition of the feed. For this case, we are going to find the boiling point. The question asks for the boiling point of your feed. Let's go back to the question. Okay. The composition of the feed is given. Calculate the boiling point of the feed. For this example, it's specifically for the feed. But if you have a multi-component distillation, I mean, this is also multi-component distillation, but most of the time, when you look at the boiling point, you'll be referring to the bottom product. But for this example, 11.72, it is specifically for the feed. What is the boiling point of the feed? Okay, so using that composition, we will substitute it in our column beside the component. So this is the composition of your mole fraction, the mole fraction. So the feed. Okay, now I know, I realize I make a mistake. Have you looked at the mistake, guys? Have you realized the mistake that I make? This is your feed composition. 90% of B will be going to the distillate. This is the second part of the example. This is 11.72. I'm looking at different example now. I'm looking at 2 different examples. That's where my mistake is. Previously, I was looking at 11.71. I'm sorry about that. I was looking at before. Is it 11.71? No, I was looking at the same example. Sorry. Okay, now let's look at this. This is not 11.72. This is not 11.72. This is 11.71. Sorry, guys. Okay, let's skip that part. Let's go back to the example. Okay, let's just look at this example, okay? You have 90% of B will be in the distillate. Okay, let me start all over again. 90% of C will be in the bottom. Okay, now let's explain it slowly. You have A, which is your most volatile. You have B, and you have C, and the most least volatile is D. Okay? So over here is mentioned that B will be in the distillate, C will be in the bottom. So that means your split is here between B and C. Okay? Your split is between B and C. So that means B will be your light key, C will be your heavy key. So A will become the light component. This will become your light component. This will become your heavy component. I'm sorry if I'm making you confused just now because I forgot that I need to do the rest of the problem. I go directly to the boiling point. I forgot about that. So you will assume that all of A will be going into the distillate. B is only 90%. 90% of B will be in distillate, 90% in the distillate. So all of A will be in the distillate, all of it. And 90% of C will be in the bottom. This is a bottom, in the bottom. And you will assume all of all of D will be in bottom. Yeah. Before you can proceed to get the boiling point, because boiling point is normally for the bottom product. So now you need to get the composition of your bottom product, not that of your feed. But if you look at example 1171, then that is a different example. If you look at example 1171, then that is looking at that feed composition. Because now I'm looking at two example actually. This is 1172. The example that I referred to earlier, that I must have a typo error there. This should be 1171. Where is it? Okay, this should be 1. So I should be looking at this composition for the boiling point if I'm looking at example 1171. But the solution that I have here in the slide is for example 72. That's where my mistake is. Okay, so this is my feed composition for the example 72. Now I need to find the composition of my top product and the composition of my bottom product based on the assumption that I made just now, that all of my component A will be in the distillate, all of component D will be in the bottom product. I have to do that. I have to make the assumption because it's not specified how many percent of A will be in the distillate, how many percent of D will be in the bottom product. So I don't know. So the only thing that I know is that 90% of B will be in the distillate, 90% of C will be in the bottom. So now I'm doing example 1172. I'm not doing example 1171. Okay, so I got myself confused because example 71 is just referring to the feed. What is the boiling point of the feed? What is the dew point of the feed? So that's my mistake just now. Okay, sorry about that. So now, look at this column. Look at the table. So this is your the mod. Let me erase this. Okay, the column here is that of your feed composition. So you will assume a basis, or is it given? Okay, it is given that the feed is 100. Yeah, your feed is 100. And it so happened that the feed is at its boiling point. That means your feed is saturated liquid. You need that information because when you want to calculate your Q, you know what is your Q already. Your feed is your boiling point. If the Q is at its boiling point, that means the feed is at its boiling point. That means Q should be what, guys? You just did your assignment. What is Q? When it is at its boiling point? When you have liquid at its boiling point, what is Q?
1.
1. You know that. So that Q, that information for Q, you will utilize later when you want to find your number of stages or your R-min. Okay? Okay, so now let's forget about the Q. Now we're going to find the composition. We're going to estimate the composition of the top and the bottom product. Okay, so the first column next to the component is your feed. And based on 100, your feed is 100 mole per hour. Okay, so you should know the flow rate for every component. Okay? You need to tabulate you need to do the tabulation. So now 90% of B, that's 0.9 times by B is here, 25. So you multiply that. If you do the calculation, you should get something like this, 22.5. So let's do the calculation. 0.9 times by 25, that's 22.5. So now you already know that value. Let me erase that so that I can just highlight it. Yeah, I have 25, so times by 0.9, I end up with 22.5. I do the same thing for C. 0.9. I know that C is 20 mole per hour based on the composition given of my feed. So time by 20, 90% time by 20 is going to be 18, is it? Oh, something is wrong. Okay, 18. Right. So where is that? That is going to be in the bottom. This is distillate. So this is distillate. Over here you have your distillate. Okay, that's your distillate. And over here you have your bottom. So your 18 is going to be here. Okay, so you will be able to know how much of your component C will be in the distillate and how much of component B will be in the bottom, because you already know what's the total the total fit. The amount of the component B is 25. If 922.5 of it is there, of course that is the 90%. Obviously the 10% will be in the bottom product. So you already know that you've got these two components for B and C sorted out. Yeah, you already know 10% of C will be in the distillate, 90% of C will be in the bottom product. So you already have this enough information. But based on your assumption just now, all of component A will be in the top, in the distillate. So over here you have 40. So you will also get 40 over here, because you already make that assumption. That is based on the assumption. Okay, and you also make the assumption that all of your component D will be in the bottom product. So you have your D there. So you will sum up. You will get your flow rate for your distillate and your flow rate for your bottom product. And based on that distillate, based on that flow rate, you should be able to get the composition. 40 divided by 64.5, you will get 0.62. 40 for component A, YD, because it's the top product, divided by 64.5, you should get, let me key in the values, you get 0.62, which is that value there. And you do for the rest. Obviously, there is no component D in the distillate, so it's 0, 0 for component D. Okay, so that's easy. Okay, and then you also assume that there is no component A in the bottom product, so that's 0 there. Okay, and you do the rest for the composition of the bottom product, and you sum it up, it should be 1. So that is how you get your composition. But this is not the final answer yet, because your calculated distillate composition and the calculated bottom composition, they are based on the assumption that all of A will be in the distillate and all of D will be in the bottom product. So now what we're going to do next, we're going to find the boiling point of the bottom product. The boiling point of the bottom product, we'll be looking at that composition for the boiling point. That is where we're going to start our calculation for the boiling point. Again, try and error. Okay, so now remember this column is the composition of your bottom product. Okay, so we're going to go to the estimate, how to estimate the boiling point. So this is the boiling point of the bottom, the composition, sorry, the composition of the bottom product. That is the composition of the bottom product. I'm not referring to example 1171. The example of 1171 is the fit. We are looking at, so I don't want to confuse you guys. So now I'll be looking at example 1172. So this is the bottom product composition. So using that composition, I will use the equation here, that equation there, to get my boiling point. Okay? To get my boiling point. So the X here is my boiling, my bottom composition. Okay, so now let's redo it again. I assume a temperature of 132. So at that temperature of 132, which is very close to 130, that's 132, the dotted line, I will get for every component the K value, which I already highlighted on the left-hand side or the y-axis. And that K value, I will write it in this column. So now that's my K value, okay, at a temperature of 132. And for that temperature, I will calculate my relative volatility. And remember, the equation for relative volatility is, let me put it over here, is equal to K of that component divided by K reference. And for this example, the K reference is equal to Kc. So I'm going to write Kc. Sorry, I'm going to write Kc there instead of reference. My reference now is component C. Okay, so based on that equation, I should get 5 for component A divided by that of C, 1.15. That will give me that value. 2.35 divided by 1.15. I should get that value. And 1.15 divided by 1.15, it should be equals to 1. And for D, 0.61 divided by 1.15. So let me tidy it up. This is very, very messy. You get what I mean. Okay, for component A, let me try to use okay. KA, let's put it here. KA over KC. And that's going to be 5 divided by, where's my KC? 1.15. And that's my KC. My B, KB, alpha B, KC, that's going to be 2.35 divided by 1.15. And obviously, Kc over Kc is equals to 1. And over here, I have Kd over Kc. That's going to be 0.61 divided by 1.15. That's how I get my relative volatility. Okay? I must satisfy this equation. My equation should be, I should get, not satisfied yet, not yet. I should get my summation of this sum, this product, sorry. I should get the summation of that product. So I will have the next column, which is that alpha of every component multiplied by its corresponding composition of the bottom. I'm going to tidy this up. Oops. Do not erase that. Yeah. So now for that column here, I multiply the value of alpha that I got from the previous column. Yeah, that's the relative volatility. I'll get it from this column and multiply it with the composition, which is that composition. So now let's look at it. Over here, I have no component A in my bottom product. So obviously there will be no value, zero value for the component A. Okay, so for the next calculation, I have 0.07 times by my K value, 2.043. That's my K value. And I do for the rest of them. And then I get my summation. My summation happened to be 0.872. Yeah, but based on the equation here, it should be inverse. I have inverse the summation. I inverse it, and when I inverse it, I got 1.14. So my K reference, my reference for C, my reference is C, component C, should be having a value of 1.144. Because based on that equation, K reference is equals to 1 over summation xi alpha I. So my reference happened to be my component C. So based on that value of my Kc, I will go back to my graph to get my temperature. Okay, so that is 1.144. Now let's go back to this graph. Where is 1.144? It's about approximately 1.1, somewhere there, somewhere closer to 1.15, somewhere there. So that means you already know that, somehow the author already know that that is the exact temperature of the boiling point. So the author already know that the temperature is going to be 132. Initially, when you this is your assumed temperature. Yeah. Now you double check with you check with this value of Kc, which happened to be 1.144, and it so happened to be almost the same as that when you use the same temperature 132. So that is that means your first estimate of that boiling point is very accurate. So your boiling point is actually 132. There's no way you can get any, I mean, you can try to get maybe it's 131. Okay, but then it's not worth it. It's approximately because we're using graphical method. How you read the graph is also adding errors to it. So 132, 131 is just very close. So we will assume that your initial assumption is actually the boiling point, 132. So now you get that as your actual temperature of your boiling point. That's the actual temperature. Because you already checked based on the calculated summation here, based on this equation, you get your new K value for your reference component, and you use the graph to check the boiling point. So now that is actually your actual boiling point because it's so close. 1.15 and 1.14 is very close. 1.14 and 1.15. How? Because you're using graphical method. Unless you have an equation to calculate, that would be better. Okay? So that is how you get your boiling point. Any questions? Anybody confused or lost along the way?
I have a
Somebody
question.
going to respond? Are you
Doctor?
still guys? Are you guys still with me?
Yes, doctor.
Yeah, okay. How about the rest?
Doctor, I have a question.
Can you please speak louder? I can't hear you.
Doctor, I have a question on the K reference. So it's not necessary the K reference will be the heavy key. K, right?
The example here, just use the heavy key to be the K reference. Sometimes it depends. Well, if you sometimes they give you the value already, that means you know that is the K reference. Sometimes the relative volatility is already given. You know that is 1. So that because that is the component, that is the reference component.
Okay, thank you,
This
doctor.
example Kc is the reference component. You can look it up whether it has to be the heavy key that it has to be the reference component. You look it up because this example uses the heavy key as the reference component. Yeah, any other questions?
Doctor,
Yes.
I have a question. If the one that we did, the 1 over alpha I xi is not equals to the K reference, then do we assume another boiling point?
Yes.
Okay, that means we have to redo the steps again, right?
Yes. You will use the next temperature that you got based on the calculated K value. The next temperature will be your starting for the second trial.
Okay.
Yeah, so
Thank you,
that's
doctor.
how it's done. It's iterative. Any other questions? So the steps, I have written it over here. Where is it? This is the dew point. This is the bubble point. Okay, these are the steps. Yeah. For that question just now, if your K value is not the same as the previous assumed temperature, then you use the latest temperature for the next iteration and repeat the whole thing all over again until you come to the very exact value or very close to the K value that calculated and from the previous temperature from the temperature that you use. If it's the same, then you proceed to the next part. The next part of the step is to get the composition of the that is in equilibrium with your liquid, the vapor composition. Remember, we are looking at liquid at the bottom product. The liquid is at the bottom product. The liquid is actually the bottom product. Sorry, let me rephrase that. The liquid is having a composition of the one that we initially assumed based on the assumption of all of component A will be in the distillate, all of component D will be in the bottom product. So that is actually your bottom product's composition. Okay. So based on that bottom product composition, you will find the vapor composition that is in equilibrium with that X composition. So if you want to find the vapor composition that is in equilibrium to it, this is the equation you're going to use. Provided you already managed to get your correct boiling point. If you haven't, if you're still illiterating, you cannot proceed to step 6. You can only proceed to step number 6 when you manage to get the exact boiling point, the true boiling point. Okay? So in order to get that composition, you have another column, okay, for all the for every component. So let's look at our solution here. There you go. You have this as your next column, based on the equation. Where is that equation? The equation is not given here. I should have copied that equation just now. Where is the equation? Number 6. So, based on this equation, I should be able to get my every composition for the vapor the bottom product is in liquid phase, but the vapor over here is the value of your vapor that is in equilibrium. Why is this X? I got it wrong. I got the wrong equation. Should be Y. This is for the dew point. I got this wrong. I should delete this. I got the wrong equation. That is for the dew point. I was such a hurry that I did not check. Okay, this is for the dew point. Okay, I should be looking at the bubble point. That's the equation. Yeah. Multi-component will be set for the final, and you can foresee that it's going to be quite a long solution because it's by trial and error. Okay, there you go. So in order to get this column, you need to use that equation. So you already have that value there, and you have the summation there. So you divide it, you will get the answer there. For example, for component A, the X, Y, A for your bottom product, the value YA, 0.143 divided by the summation 0.8742, you should come up with 0.164, which is that value there. Let's double check. Okay, the answer is if we use 4 decimal places. Okay, there you go. So that's how you do for the other components, and you should be getting a summation of 1, obviously because it is more fraction. Okay, so that Y value is important because it is in equilibrium with your bottom product. When you look at the column, the bottom of the column, this is your reboiler, partial reboiler. This is where your bottom product is coming out, having that composition. So since you have many components, so you will have component A, B, C, D, and so forth. And this is the vapor that is going to be boiled by the partial reboiler, and that will have the composition that is in equilibrium with the X. That is your, well, give it a subscript of Y. That vapor is in equilibrium with the bottom product. This vapor is in equilibrium with this bottom product. That's why it's important to get the composition of your Y. Yeah. Any questions? That is just the bottom product. We'll be doing the same thing for the top product, okay, which is getting the dew point. So now let's look at the dew point. This is how you do the dew point. Again, try and error because you don't have the exact value for the component A in the top product, and neither do you have the exact value of the component D in the top product. So it's again try and error. So what you have to do, first you assume a temperature for your dew point. Okay? And from that dew temperature, get the corresponding K value, Again, the same thing, same procedure from the graph or from the equations, and calculate your relative volatility based on whatever reference K you're going to use. In this case, in this example, you're going to select component C as the reference component. Okay, and then because of this equation over here, you need this summation. Okay, so do that calculation in one of the column, and then get the summation. Okay, so if you rewrite that part of the equation here, if you rewrite it, oh dear, I think I got wrong here. Should be 1, not y. I think I got it wrong. Let me double check. Okay, where is my dew point? Should be 1. Should be 1. There's a typo error there. Should be 1. Okay. Somehow I copy and paste from here. It become there. So that's my mistake. So please do make the correction. 1 over K reference. So if you do this, hold on. Let me highlight this. Okay. So from that part of the equation, you will get K reference is equals to, bring this over there, summation, hold on, 1 over, let me double check my equation in the textbook for the dew point. Yeah, I got it right. That is the equation is like this, 1 over K reference, summation yi over alpha I equals to 1. That's that equation there. That equation there. Now, I need to find K reference. Should be what? What should it be, guys? Do the mathematics. Somebody? Should it become 1 over summation yi over alpha I? Should it become like that? Is that the answer?
Yes,
yeah. Okay. So based on that, you will get your summation of the summation here. Okay? And then calculate your K reference here. And from that K reference, you will get your corresponding temperature. From that corresponding temperature, if it so happens that that temperature is the same as the one that you assumed earlier, then that will be your final dew point. If it's nowhere near, then use that latest temperature for your next second trial. And if you want to get the liquid composition that is in equilibrium with that vapor, that is the top vapor, then use this equation. Yeah. Let's look at the example for example 1172 for the dew point. This is it. Assume this is the temperature, dew point. Obviously, the top temperature will be much lower compared to the bottom temperature. Okay, because the top temperature has a composition, most of it will be the lighter component. Most of it will be the lighter component so that they are most volatile. So you have lower boiling point. I mean, the component that is at the top, most of it is the component A and B for in this case. And you don't have any D. So the temperature will be lower. So for the bottom component, for bottom product, you have most of it is the higher boiling point component. So the temperature at the bottom will be higher. Okay? So now you assume 67 degrees C. So at 67 degrees C, I have over here roughly 67 there, roughly. I will get the K value for every components. Okay, in this case, we are dealing with N-pentane, N-butane, N-hexane, and N-heptane. Okay, so with these values obtained from the graph, I'll have it listed here. Okay, the composition for, where is my composition? I should be using the composition Y. I should have one column here, Y, I, which is the top composition, the top product, the distillate that we got earlier. So I should have one column there. How come it's missing? Yes, that is the top composition. That is the top composition. I should have that column next to my component here. I should have it. Somehow it's missing. Why is it missing? So let's just draw our what? Put it, insert it over here. Okay, my component, let me get it from what I'm trying to do. I can easily just copy it. What I'm trying to do, I still forgot that I have the facility to copy it and paste it. I have that facility. Okay, I should just copy it and bring it over. No, I'm not looking at the bottom. I'm looking at the distillate. This is the distillate. Yeah, I should just copy it. I should not bother to write it because I have that facility. Okay, I don't have to do this. I just paste it. Okay, there you go. Okay, that's done. That is my distillate composition. Okay, so now for my K value, here, I selected my Kc to be my reference component. So I will get my relative volatility equals to 1. Remember, relative volatility is calculated according to this equation. Ki over K reference. My reference is component C. So 1.75, this is equals to 1.75 divided by 0.26. I should be getting 6.73. That's very messy. My K value, 1.75 for component A. My K value for my component C, 0.26. So that's how I get my alpha for component A. And I do the same for the rest. Okay? Now, because my equation specified that I got to get this equation just now for the dew point, so I will get this column here. I get, where is my composition? My composition is this value here, divided by the alpha value, that which is this value here. So I will have this column here. And the summation, when I do the summation, this is what I get for the summation. I must satisfy this, I will get, not satisfied, sorry, I must get this value for K reference. In this case, my K reference is Kc. So if I do the summation, this is a bit weird. You know why? Is it 1 over summation? Is it 1 over or is it summation of that? Okay, but go back to the equation just now. I must have, this is wrong, isn't it? That's why I was asking you guys, is that right just now? Is this right? Is this right? I was asking you guys just now, is that right?
I think is the one in the one at the solution is correct, because if you pindah because if you do some rearrangement,
This one over there, isn't it?
and then when this go over there, because this the denominator.
Yeah, you know, this is wrong. Why this is wrong? Because I copy and paste from the bubble point. This is bubble point. Look at it, y1, yi divided by alpha I. This is wrong, because somehow I must have copy and paste. I got it wrong here. It's correct. Somehow I got it wrong. It should be, sorry guys, there seems to be something typo error here. Should be K reference equals to that. Okay, so that should be here. There's a typo error here. There's no inverse of it. Okay, please correct that. There's a typo error there. I need to correct my slide. There's a typo error. Obviously, because when I asked you guys, you said, "Oh, it's correct." So I thought it was. My instinct was telling me. It's wrong. But since you say it's correct, okay, I trust you guys. So that is the answer. So now your reference for the dew point, your reference for the KC is going to be This is not, but this is bubble point. Where's the dew point? This is the dew point here. Okay. This is the dew point. No, no, no. Where is it? This is bubble. This is dew point here. Okay, here you go. So it should be that summation. Your Kc should be here, that value. And it so happens that your Kc earlier when you get at that temperature is the same. Roughly, it's about the same. Because the author already know that this is going to be the dew point. Just use the first trial. He's not going to do too many trials. Right, so this is your initial K value at the temperature of, assume of 67 degrees C. And when you calculated it using the summation, it so happened that it's very close. So this temperature that you assumed earlier is actually the correct temperature of your dew point. If it's not, then use the next temperature to do the second trial. Seem to be many typo error here. Okay, now for the corresponding X composition that is in equilibrium with the bottom product, you use the equation which is from number 6 here. Let me go back to the steps. There, use this equation. Use that equation. So if I copy it, if I copy it and bring it over to the example, there you go. How to get X? You use this equation. That X here is obtained using this equation. For every component, you will do the same. So you have that component X in equilibrium. And so when do you need that equilibrium X component? Okay, let's look at your top of the top of your column. This is the vapor coming out of the column, going into your condenser. Part of it will be going back in the as a reflux, and this is your bottom your top distillate product. This is your vapor V1. So when is it in equilibrium? Anybody? When is it in equilibrium? When is this Y1 in equilibrium with that Xi that you got just now? Anybody? This is XD. This is, for example, L. This is also XD. If that is a total condenser, your XD and your Y1 should be the same, isn't it? If this is a total condenser. Is that the fact? Is that the case? Is that the case? Should Y1 be equals to same as XD? We are using a total condenser. Anybody? Is it the same? Okay, let's give an example. I have my cup of tea. Initially, it is okay. This is not really a good example, but well, this is something that's come to mind at the moment. I have my cup of tea. A certain composition of the tea inside the hot water. If I decide to change the temperature, instead of that, initially it was warm. Now I want to get it frozen. I put it in the freezer. Will the composition be the same of that cup of tea? Will it be the same, even though there's a change of phase? Initially it's liquid, now it's frozen, solid. Is it going to be the same, the composition? Anybody? This is not a good example, but I'm just trying to, that's the example that comes to mind at the moment. Is it the same, the composition?
I think it's same, Doctor.
Yeah, it should be the same because I'm just freezing it. The same case here when I'm using a total condenser. Initially it's liquid, initially it's vapor coming in. Now everything coming out is liquid. So the composition should be the same. I'm just changing the phase. Okay. But if I'm using a partial condenser instead of a total condenser, I'm using a partial condenser. I did mention this last time. We did look at this when we are looking at the binary distillation. Now this is a liquid. This is D is in a vapor phase. This is YD, the vapor phase. But your liquid coming in is in a liquid phase. Your reflux is coming in liquid phase. So your reflux here, composition here, is going to be this in equilibrium with your liquid, your gas. Sorry, your gas. Sorry, this is not the same. This is not the same there. Not the same here, but it will be in equilibrium here. It will be in equilibrium there. It will be in equilibrium. So that's why you need to find the liquid composition when you're dealing with partial condenser. Any questions so far? I seem to be getting typo error for my steps here, so please correct it. Yeah, correct this information here. My instinct is already telling me that it's wrong when I wrote it, but somehow I wasn't sure, so that's why I asked. So this is the correct. This is the correct question that should be in for step number 4. Yeah, that's the correct question. Somehow I got it wrong. Somehow I must have copy and paste. The error is from the copy and paste thing. Again, the same here over here. That's 1 there. 1 over. Okay, so correct it, please. Any questions? We haven't yet checked our assumption. Any questions so far? Any questions? You will not have to do any try and error. The solution will no longer be try and error if you know the exact value of what is going on, what is going into the distillate, and what is the composition of the distillate, and what is the composition of the bottom product. If you are given enough information that everything is there for you, the information is there, that you don't have to assume anything, then you don't have to do the try and error method to get the composition, I mean. But you still have to do the try and error method to get the boiling point and the dew point. If you are asked for the dew point and the boiling point. But in order, if you are given enough information whereby you don't need to make any assumptions for the composition of the distillate and the composition of the bottom product, then that saves you from the making any assumption. Initially, we did assume what is going on, how many all of component A will be in the distillate, all of component D will be in the bottom product. We make that assumption. So you need to check your assumption. So before doing that, any questions?
Doctor,
Yes.
for key reference value, let's say I choose KC for key reference. So if my key reference value is almost the same as total yi over alpha I, so does that mean TDP assume is almost to the accurate value?
You're
Or
looking at the dew point, is it?
yeah.
So can you repeat that again? This is the equation.
So let's say my key reference is C, and then the value it shows that 0.26, almost the same as sum of yi over alpha I. So does that mean if my value is almost the same, my TDP assume is almost accurate to the real TDP?
Yeah. Initially, you assume that this is the boiling, the dew point. And at that dew point, you get it from the graph. Get it from the graph, you get this value. Get that value from the graph. And when you do the summation, this is the value that you get. So both of them is very close. So that means you got the correct dew point when you assume earlier.
Oh, so if the value is lari ke, so that means my TDP assume is wrong.
Your TDP, that means now if it's no way close, your K reference, you calculate based on this equation, and it's no way close to the calculated assumption here, and no way close from the K that you got earlier. Okay, it's no way close. That means now using that calculated value for your K reference now, from that K reference, you get it from the graph. For example, let's say, just give an example. For example, I got this. Now after I calculated it, I got that. Now I go to my C component and I will get my new temperature. At that new temperature, I will start all over doing the calculation with another table. With another table, I do the same thing. I repeated everything, and I will shoot. And lastly, I will check again whether my K reference is going to be the same as the at that same temperature. I assume this is going to be your second trial. Does that answer your question?
Yes, thank you.
Okay. So using the second temperature, the temperature that you got from the graph, based on that K reference that you got from that K reference, then you will use that. Did I make a mistake again? So this is based on this equation, isn't it? Okay. So if based on that reference, then I will get another temperature. This is boiling point. This is dew point or boiling point? I got confused. This is dew point. I got the wrong equation here. This is the wrong equation. This is for boiling point. This is for boiling point. Anyway, guys, check. Somehow I got mixed up. Just now we are talking about dew point. This is boiling point. This is boiling point. This is boiling point. Somehow, you better check. Somehow my this one is referring to dew point, but my equation seems to be not the equation for dew point. Please check. Yeah, the equation for dew point is confused. This is the equation for dew point. Yeah, this is equation for dew point. It should be x. Should be x. If no, it's y. So it should be for boiling point. This is the equation for boiling point. That's the equation for boiling point. This is the equation for boiling point. Got confused between the two of them. I have copied the wrong equation. This is the equation for boiling point, and the equation for dew point is this one. This is the equation for dew point. You have the x there. But you get the point. The point is that you must satisfy this equation in order to get the K reference. Yeah, if you get the K reference, then you get the new the corresponding temperature. If your temperature that you assume and the temperature that you calculated from this that you get from this equation is the same, then that is the correct temperature. Or the K value is if it's the same, then that's the correct temperature. So it's either way. You can look at the temperature or you can look at the K value. When do you check for your actual composition? You will check somewhere along the way. Yeah, you will not do yet the checking the composition. You will only do it here based on that equation. You need to get your minimum number of stages first. This is when you need to check your assumption. When you assume that all of component A will be in the distillate, all of component B will be in the bottom product. So this is when you will know what composition is actually in your bottom product, what composition is actually the distillate, in the distillate. Okay, so any other questions? This is going to be a very long, to calculate this is not that long, minimum. To calculate the minimum number of stages is just straightforward, putting in the values. you're going to use Fensky equation. But before looking at that equation, any questions based on the try and error method for the boiling point and the dew point? I seem to be making lots of mistakes this morning because I was referring to the wrong equation. The boiling point is here, correct? The equation is correct. The equation is correct here. Okay, somehow I got mixed up between the two equations, boiling point and dew point. This equation is for the boiling point. Okay, this equation, the one that I got here, is also referring to this example, the boiling point. And the equation for that is for the dew point. Where is the equation for the dew point? Where did I put it? I did not put it there. I did not copy it. So the equation for the dew point is not there. So this equation just now, this equation that I'm zooming in is actually for the boiling point, which is for that part of the slide. So I got it correct. I thought I got it wrong. Any questions? In your final, I'm supposed to set this multi-component distillation. Yeah, I'm not going to give you 4 components. It's too long. So instead, I'm going to just give you 3 components. I cannot give you 2 because 2 is binary. Multi-component distillation is supposed to be more than 2. So I'll just give you 3 components. Yeah. And you have to go through the whole process. But it's actually, there's no try and error because the composition has been set. For the composition, there's no try and error. Okay. For the final, the question for the final. Okay, now, I'm going to look at how to calculate. We're going to look at how to calculate the minimum number of stages. Okay. So if you look at this equation, I can cancel the distillate there, I cancel distillate there, I cancel the W there, I cancel the W there. I will simplify it. It will become, I can also use it in terms of log, natural log, sorry. If I got the denominator and the numerator using the same, then I could use log or natural log or natural log. So what I will write for natural log, XLD, XHD, I will explain what the subscript stands for. XHW, but I think you already know what they are. XLW. Okay. Divided by the average, the relative volatility of your light key. And how to get the relative volatility of your light key? You have this equation. The relative volatility of your light key is the relative volatility of the distillate, the light key in the distillate, the light key in the bottom product. So that's the explanation here. Yeah. So this is your light key. That's your light key. That's your light key. That means for the example that we were looking at earlier, that will be component B, your light key. Okay. Your heavy key, let's use a different color. That is your heavy key. That is your heavy key. Your heavy key, if it has a subscript D, that will be in the distillate. If it's subscript W, it will be in the bottom product. Okay. So if you look at the light key, this is your distillate, that's in your bottom product. This is obviously average. Okay, so the average can be calculated. The square root of the light key in the distillate multiply it with the light key in the bottom product and get the square root of it. You get the product of the relative volatility of the light key in the distillate and in the multiply it with the bottom product and square root it. So let's look at the example that we were looking at earlier. Where is the relative volatility in the distillate? Relative volatility of your light key in the distillate. Okay, this is your distillate. This is your distillate. And this is your bottom. This is your, okay, sorry. Let me extend this. This is for your distillate. Okay, that is for your distillate, which we got earlier when we were doing the boiling point and the dew point. Okay. When we assume at that temperature, what is the dew point, what is the boiling point. When we finally get the final answer for the boiling point and the dew point. These are the values that you got, yeah, at the actual dew point and boiling point. So now your light key is component B, and this is in the distillate. Okay, and this is in the bottom product. So that is going to be your XLD. That is going to be your XLW. Sorry, not X. We are looking at relative volatility, not X, but alpha, relative volatility. Okay, so substituting that inside this equation here, you get the average relative volatility. 2.5 times 2.04 square root it, you get that value. That is your average value. So if I'm going to copy this equation, let me copy it. Bring it down here. Have the equation. I'm going to calculate my N mean. Okay, so my light key in the distillate, the composition of my light key in the distillate, my light key in the distillate is this. Yeah, I'm going to substitute it here. My composition of my light key in the distillate. Next, I'm going to look at my light key in the bottom product. My light key in the bottom product is, the composition is here. Okay, I'm going to use a different marker for my, this heavy key in the distillate. Heavy key in the distillate. My heavy key is C in the distillate. This is it. And my heavy key in the bottom product. My heavy key in the bottom product is here. Okay, so I have enough information to calculate my N mean because I already managed to get that value for my average relative volatility for my light key. But enough information, so now all I have to do is just plug in the values inside the equation. My XLD, okay, my XLD 0.349 divided by my heavy key in the distillate 0.031 multiply with my heavy key in the bottom product 0.507 divided by light key in the bottom product 0.070. So that natural log divided by the average value of my relative volatility, which we obtained earlier here. So natural log 2.258. How to get that? I already explained how to do it. Yeah, so I did explain this is my relative volatility for the light key in the distillate. This is my relative volatility, the relative volatility in the of the light key in the bottom product, which we substituted there. Okay, so we got that 2.258. So my N mean, my number of minimum stages, if we do the calculation, so I'm going to double check, which is actually the same as that, which is the, over here we have log log. So now I'm going to do it natural log. Oops. Got 7.29. Don't have enough space. Yeah, let's just write over here. Okay. Natural log 2.258. I'm going to erase this. As mean equals to 4.4011 divided by natural log 2.258. Zero 0.814415. What's the answer? I got 5.4. or 3? What's the answer? 5.4 or 4. Okay, that's close. Same value, obviously, because we got it from the same example. Obviously, you should get it the same. It's just that I'm using, instead of log, I'm using natural log. Okay, so you can use both methods of either way, using log or natural log. You still get the same answer. Now, once you manage to get your n mean, you will use this equation, which is that equation at the bottom here, to calculate the distribution of component A and D. Remember A and D you assumed earlier. So you're going to use that to recalculate the composition. So I'm going to put it over here. That's the equation. Okay, so I need to do for component A in the distillate times by the distillate flow rate, component A in the bottom product times by the bottom product equals the flow rate of the bottom product, the relative volatility of component A, the average value, and time to the power of n mean. There should be n mean to the power of n mean. Let me check the equation. There seems to be a fact there. Yeah, n mean. And then this thing is here. There. This is the power of n mean. That's the power of n mean. And then this whole thing, x h d e x h w w. Okay. This is your heavy key. But you're going to solve for component A because the component A is the one that you don't know. And you do the same thing for component D. Because the component D is the one that you assume earlier. That will be relative of component D, average, to the power n mean. X, H, D is still the same. D, X, H, W, W, still the same. So now, what is the average relative volatility? You're going to use the same equation that how you got just now for the light key. Let me delete this first so that I will copy the light key, this equation. I'm going to copy and put it over here. Okay, now, this is specifically for light key. So I'm going to replace it. I'm going to put for component A only. Why am I cannot write there? Okay. A only. Component A. Yeah. So if I'm going to do for component D, I do the same thing. Square root it. So component A and D are the one that you assumed earlier. So you have to double check your calculation. This is how you do it. Your n mean is the one that you just got earlier. That is, where is that value? Okay, let me highlight. That is the n. That is the value of your n mean. So this is the power of. Right? So if you check this calculation, this is how it's done. That's the power of. That's the n mean. Right? Your average value is not. For this part should be the same for both the equation. But they are the same here. If you look over here, they are the same. Even though we're looking at the component A or component D, they are the same. So you can get your composition of the heavy key in the distillate. This is the composition of the heavy key in the distillate. Let me write that heavy key in the distillate. Okay. Composition of the heavy key in the bottom product. That is the composition of heavy key in the bottom product. And so you should be able to substitute it there, inside this equation. And the D, the value of D, flow rate, the flow rate of the distillate, and the flow rate of the bottom product is there. So you should be able to substitute it there. Okay? So how to get these values? Alpha A at the distillate and alpha A at the bottom product. So you have to get it from, this is alpha A at the distillate, okay? And this is alpha A at the bottom product. So get the square root of them. Get the products and get the square root of them. For D, this is alpha D at the distillate. This is alpha D at the bottom product. So get the square product and then square root it. So you should be able to solve that and solve for that. And substitute it here and substitute it there. Yeah. And then solve for your individual component. This is the composition that you need to solve for the left hand side. If there's a continuation of it, okay, there you go. Okay, this is the relative volatility of component A. This is the relative volatility of component D. So when you substitute it inside this equation, you end up with that value there, that value here. Okay? This is over here, this is over there. This part is the one in the bracket, this part. Okay? Now you have this whole thing equals to that equation, and this whole thing equals to that equation, to the left right hand side, sorry. So you know by material balance, if you're looking at component B only, component A, material balance of component A only, you have XF times XF for component A is equals to X of D, component A, times by D, plus X of component A in the bottom product. So that is your first equation. So this is that part of it. Yeah. And you're going to solve it simultaneously, the two of them. You do the same thing for component D. You have X, F, D. You have X, sorry, equal sign. Component D in the distillate plus component D in the bottom product. Okay. That is your that is your third equation. This is your second equation. You compare, you solve simultaneously 1 and 2, and for this is your let's see, this is maybe your fourth equation. So you solve simultaneously the two equations, 1 and 2, 3 and 4. You solve it simultaneously, you will end up with the final values here. You get out these final values. And you will put it inside your table, substitute inside your table. Now you have the table now, new table. Okay, just for component A and D, just for A and D. The rest, B and C is still the same because you did not assume anything for the B and C. So now you substitute the value that you got. For example, this value here, that is for the distillate of component D. So that is 0.026. So 0.0, where is it? This is your earlier assumption, the one that you use, assume all of A will not be in distillate. So none will be in the bottom product. Okay. And all of D will be in the bottom product. Whereas all of D will be in the bottom product. So all of D will be in the bottom product. This is the assume table. So this is the table that you use, that now you're going to substitute the calculated value. So your calculated value, for example, I'm looking at this. That is for the component D in the distillate. Component D in the distillate, so this is it, 0.023. I put it there. And then my component D in the component A in the distillate, component, sorry, no, not A, yeah, it is A. Component A in the distillate, component A in the distillate, that is it. Okay. So now I total it out, I get my flow rate. Now there is a difference. Initially 64.5, now I got 64.484. And based on that distillate flow rate, I should be able to get my composition for my distillate. And for the others, for example, this is the bottom product, component A in the bottom product. Component A in the bottom product is 0.0349. Then this is the component D in the bottom product. This is it. So I total everything up, I will get that flow rate for my for my bottom product. And I will do the calculation for the mole fraction. So now you can see there's a small difference. Initially, when you assume you got 35.5, this is your initial assumed value. All of D will be in the bottom product, but instead it comes to be 14.977, quite close to your assumed value. And that just change your flow rate for the bottom product. And when you assume that all of A will be in the distillate, but it turns out that not all of it will be in the distillate. Some of it is still going to the bottom product. So this is not exactly 40. This is 39.961. The rest, the very small portion, a very trace amount of it will be in the bottom product. So when you sum up your flow rate for the distillate, you will get your mole composition. So there's a very slight difference. You can see there's a very slight difference. A very small difference. Now you have to calculate the mole fraction for the mole fraction for B and C you need to calculate too. Because now the flow rate changes for the D. So you need to calculate that too. It's not the same now. Okay, so any questions? Your assumed composition is at the top. Yeah, that is your assumed composition. Now it changes because we already recalculate the distribution of the other component, which is component A and D. So it changes. So this is your actual composition of your distillate and your bottom product. It's quite close to the assumed value. Any questions? Very long. The solution is very long. We haven't even finished yet the whole steps of it. The next step will be to get R min, to get the number of stages, and then to get the feed location. There's number of stages and to get the feed location. Yeah. We're only just halfway done. Any questions? Any question, guys? Are you with me?
Question,
Yes,
Doctor.
Doctor.
Yes. No questions? Okay, let recap what I did just now. I calculated the number of minimum stages using this equation based on my assumed composition that I got earlier. I calculate my average relative velocity for the light component based on this equation, based on the dew point and the bubble point temperature that I got earlier, the actual bubble point, the actual dew point. Right? So once I have done that, I need to bracket this. Okay? And you can see that this is to the power of n min is to the power of. So I will calculate the actual composition of component A and D, because component A and D initially I assume that all of A will be in the distillate, all of D will be in the bottom product. Now I will have to recalculate my assumption, check my assumption using this equation. This is where I'll get the two graph that I show here. The initial assumed graph, sorry, not graph, the table. The initial assumed table is at the top, and the actual the distribution of component A and D in the distillate and then the bottom product is at the bottom table. Right? So that's what I did just now. So in these 2 hours, I have done the calculation for the dew point, the calculation for the boiling point, and I have calculated the minimum number of stages, and I have revised the composition for the distillate and my bottom product. I recheck my assumed value is quite close to my calculated value. Right? So that's what I've done today in 2 hours. So in your final, 2 hours is a long, not just for one question, too long for just one question. You have 3 more other questions that you need to solve. You need to be very, you need to know your stuff very, very well. Same thing with test number 2. Even though you have 2 questions, 2 questions is 1.5 hours. You really need to know the stuff. Because if you're still struggling, you'll be wasting lots of time. Yeah, especially if you have to plot graphs, that will take I mean, obviously you have to plot the graphs, and that is really time consuming. So unfortunately, your multi-component distillation is going to be in the final. So bear in mind that these steps, they are very long. So you really need to know your stuff. That you don't have to, that means you know it and you will just proceed and do it without having to flick back and forth, trying to figure out how to do it. Okay, guys, it's almost 1 o'clock. So thank you very much for your time. For those who haven't scanned in your attendance, I will share the QR code again. So I will be giving you guys the multi-component distillation, the assignment for it. In fact, you can do at the back of the chapter 1174. No, second. Problem 1174. You have the same component like the example. You need to do it using maybe different percentage of recovery, different composition of feed. So that is problem 1174. So I would suggest that become your assignment number 4. Problem 1174 will become assignment number 4. Yeah, I will not give you the assignment in e-learning. I'll just mention it here. Problem 1174 is your 4th assignment. Yep. It's just one problem, but you have all these things, the subs part of the question that you need to answer. Okay, guys. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doctor.
Thank you, Doctor.
Stay